Section 10.5 I think is going to make some sense to you. We're going to return to some of the ideas that we saw when we first were moving between the rectangular plane and the polar plane. But what we're going to do is we're going to do it similarly, but this time with complex numbers. So what we've seen so far is that we have this rectangular Cartesian system that we've been using forever, and we're so comfortable with it, it's easier to refer everything else to this. Then we saw how we could move into the polar. Well, do you remember how the complex plane worked? We're going to move complex numbers into a polar setting here in a minute, but to graph a complex number, so first of all, a complex number has this real portion, which we would call A, and B is that imaginary portion. Remember, at the root of it is the idea that I is equal to the square root of -1. And so what they developed was that math could continue working even though we're not allowed to have a negative under a square root. The math continued to work. So I have this complex number with a real part and an imaginary part, and we could graph them. Do you remember how this worked? We would treat the x-axis as the real portion, and the imaginary axis becomes the y. So the complex number 2 minus 3i goes 2 to the right, because the 2 is the real portion, and down 3 into the imaginary. Now we're going to convert these in just a bit, but let's get back to make sure you remember how to do this. So the real portion would be 1, and the imaginary portion is the y, so I'm going to go up 5. Okay, so we're going to find the value, the absolute value of a complex number. And so all we're going to need to do here is we're just simply going to treat it as if it's a diagonal, which we've been doing forever. So if here's the value, what we're going to do is we're going to find the hypotenuse. We're going to imagine it's a triangle, just like we did with polar before, like we've done many times in this course. So in order to find the value of this imaginary or this complex number, we're just going to do the Pythagorean theorem here. We're just going to find the value of what the hypotenuse would be. So let's take a look at one. So if I want to find that absolute value of that complex number, it's just going to be the hypotenuse, which would in this case would be, well, the square root of 5 is the real portion, we're squaring that. -1 would be the imaginary portion, we're squaring that. And so do you see how we get down to the square root of 6? Okay, how about this? Let's try another one here. So we want to find the absolute value of a complex number. It's the hypotenuse. That's what it is. So we're going to square 12, and we're going to square -5. So I'm going to get 144 plus 25. So I'm looking at the square root of 169, which is 13. Now we wanted the absolute value, so it's just positive 13. Okay, let's find it again here. We're just going to find the hypotenuse. That's all it is. So square 3, square -4. Simplify that down, we get 5. Okay, we'll do this one more time here. Absolute value of z is going to just be 1 squared plus -7 squared. So 1 plus 49, the square root of 50. Now we could simplify that down. That's made up of, do you remember how to do this? 25 times 2 is one way we could do it. It's going to be 5 square root of 2. Okay, now here's what the main thrust of this was. We are going to convert these complex numbers into a polar form. So we went between Cartesian, the rectangular system, into polar. Well, imaginary numbers could do the same thing. But the premise is identical. It's exactly the same concept. The only thing now is that this y-axis is an imaginary axis now. It is not the same as our traditional y, but the conversion is based on all the same ideas. It's going to be a triangle is going to get dropped here, and if that's the case, then x can be r cosine of theta. So remember, theta would be, so if this is cosine of theta, it's adjacent over hypotenuse, and solve for x. And if you did sine of theta, it would be opposite over hypotenuse, which is how we could solve for y. And then r is going to be the square root of x squared plus y squared. It's going to be the Pythagorean theorem. So the same exact conversion. So we want to get into thetas and r's. Okay, so look at what happens here. So this is a complex number, x plus yi. Now, what we can do here, we're just going to replace x with r cosine of theta, y with r sine of theta. We've done that before to convert to polar. And so now a complex number can be written, they just pulled out the GCF of an r, can be written like this. Now, this is a little bit much, but our textbook is going to call this, well, I'll wait till we see. Yeah, here it is. They're going to abbreviate this r cis. So for cosine, imaginary number, sine, just to abbreviate this because it's just writing the same thing over again. And the angle is the same for both. So if you see this, I'll reference this again. It's just an abbreviation, or maybe I'll show some here. But so here's our conversion. It's exactly the same concept we did when we went into polar last time. Except, again, the only difference is that the imaginary portion is, the y-axis is the imaginary portion. So, again, here we have all the same things. This, then, is a complex number in polar form. Okay, so let's do a couple of these. So, the first thing we're going to need to do to switch this complex number into polar form is we're going to need to find r. And finding r is simple. It's just finding that absolute value that we've already done. It's finding the hypotenuse. So there is no real portion this time, so it's 0. And the y portion, the imaginary portion, is 4. So if I square that, get down, it's going to be 4. Okay, now we need the angle here. So there's a couple ways. We're going to do some different ways in just a minute. But remember what this graph would have been? The original graph of this complex number would be right here. So the angles work the same. If like our unit circle was in there, we move up here. Isn't the angle for this pi over 2? So there's some other ways we could have done it, but this is the easiest way for this one. So r was 4. We just find the hypotenuse here by x squared plus y squared. Then look at the angle. It has to be pi over 2 because it's right on the y-axis. So here's how we write it. We know r, cosine of the angle plus I sine of the angle, which they'll abbreviate sometimes. I would just write it out so it's not confusing to you, but here's the abbreviation. 4 cosine imaginary number sine of pi over 2. Okay, let's do another one here. So the first thing we need is r. So we need, there's no real portion, so we're just finding a hypotenuse. There's the imaginary portion, so we've got r is equal to the square root of 9. So r is going to be 3. Now, just like we did before, this one's easy. We'll get to some harder ones here in just a second. But what's the angle that this point is at? Well, it's right there on the y-axis. So once again, our angle is pi over 2. So in polar form, we get 3 cosine of pi over 2 plus I sine of pi over 2. All right, let's do a little harder one here. So we find the value of r the same way we did. This isn't going to be harder. And we just plug it in there, get down, we get r is 4 radical 2. Now, now they use cosine. I don't think that's the best way to do it. So let's do, when we've been looking, exactly like we did before, when we've been looking to try to find the angle, the tangent of theta is going to be y over x. So I'm going to put in, and y in this case is the imaginary part. So I'm going to put in 4 over negative 4. So when does tangent of theta equal negative 1? Now, you probably didn't know these when we got started, but you started to see this tangent is 1 at pi over 4. It's negative 1 in the second quadrant, which is 3 pi over 4. So we have our angle. It's 3 pi over 4. So we have everything we need. So z in polar form is going to be 4 square root of 2 cosine of 3 pi over 4 plus I sine of 3 pi over 4. All right, let's do another one here. So first thing we need is r. So we're going to have the square root of 3 squared, that's the real portion, plus 1 squared. And you see this is going to turn into 3 plus 1, so the square root of 4. So square root of 3 squared is just 3, plus 1. So that's going to be 2. Okay, so I have r. So now we're going to use tangent, just like we did earlier. Tangent is going to be the imaginary portion, in this case is 1 over the square root of 3. Now, I'm not going to go ahead and rationalize that. I want to know, when does tangent become 1 over the square root of 3? Well, that's sine over cosine. Cosine. And that's going to happen if sine were 1/2 and cosine was radical 3 over 2. That happens at 30 degrees. So, in interval, or in radians, that's pi over 6. That's 30 degrees. So this happens at pi over 6. Now, why did we settle on pi over 6? Perhaps we should have picked the third quadrant. Well, look at this polar point, so, or what this original point would have been on a complex plane. Positive, positive. We would have been here in quadrant 1. So this is what we wanted. We wanted pi over 6. So let's write it. So z in polar form, 2 cosine pi over 6 plus I sine of pi over 6. Okay, I hope this makes some sense. It's following exactly the same pattern that we saw when we just moved rectangular into polar. Everything is identical to that, except now the y portion is now the imaginary portion of a complex number.